All right, before I get started, any questions on anything we did last time? Okay? Now, last time we did talk about things like the syllabus, research paper, locator card, all that kind of stuff. I've got the first of that loaded on Blackboard now, so that's why I started with Blackboard. Now, I don't know if yours looks just like this, because this is the instructor side. The student side may be a little bit different, but here's where I put things. You see this third blue tab down here? I think I told you before, I put things under class handouts and more. But since I found these, I said, well, let me put the syllabus under syllabus. So when you click on that, and this is our class, there you'll see syllabus. Click on that, and you got the syllabus in front of you. I hope I made all the corrections. So remember, if you do click on this, I don't know why it's not clicking. Seems not to be wanting to cooperate. Oh, maybe you click here. Okay, that will do it. Okay. I thought it should click on syllabus, but some of them it does. Okay. I want it to open and allow. Oh, goodness, this is such a pain in the neck. Okay. Goodness gracious. I guess this is on the instructor side. You probably don't have to do all that. I guess that's to keep people from getting into the instructor's thing and changing things. So I guess that's why I have to do all that. Well, I thought this would come up. It doesn't look like it's there. It comes. Maybe. Possibly. Let's hope so. There we go. So there's the syllabus. Okay? And I'm not going over it again, but I hope I made all the corrections in it. It seems like to me I had most of everything corrected and updated right down to college calendar. And that's the stuff I've updated today, so I hope that's right. Now this is for first mini-term. If you're in a full-term course, not all these dates apply to you. These are only the ones for first mini-term. Okay, and that's what we are. So if when you've read and gone through the syllabus and you understand it all, you don't have any more questions, if you have questions, come ask me. Then please print or sign and date, whatever you want to do, this page, turn it in to me. Okay? You can either type it in and email it to me, or you can actually copy it, print it, and then sign it and put your, if your signature is really bad, then print your name as well, and then date it and give it to me. Okay? Any questions on syllabus? All right. Then we'll get out of that one, and get out of that one. And then the teacher info and office hours. That's where I decided to put my locator card. Now, I didn't have this done last time. See, that you can click on. The other one you had to click on the other part. Okay? And we want to open it. I don't know if yours require all this. Allow. Okay. And on mine, the download takes a while. I'm sorry, so I didn't want to show it to you, so at least you've seen it. Well, there we go. No, I have to do this. Do y'all have to do this every time you open Blackboard? Okay. I was hoping you did.
Depending on what part of Blackboard
you're at. Yeah. And I think because this is the instructor side, you have to go through all that safety issue. Protection. Okay, there's my locator card. Okay? And I talked about it before. Here's how it looks. I think I've got everything on there correctly. So that shows when I'm on campus, when I'm in class, when I'm in the office, when I'm off campus, when I'm having lunch. So you can always come by during lunch. Those are usually, I count those office hours as well. So I think all that you need to know, in which campus I'm on. Always on Bastrop campus, except for Wednesday afternoon, travel to Birmingham East, and I'm there until the end of the day. And then on Friday, I'm on office hours on Birmingham West campus, academic building B122. That goes up until 11, though. You can come until 12, because I usually eat lunch. I don't eat a full lunch, so I'm usually through pretty soon. But I can snack in. It's just usually a snack. So, but I'm off campus sometime after noon. So, all right, so that I think gives you just about everything you need there. All right, now the rest of it isn't complete. I've just barely got, well, I don't want that. Sorry. Okay. The rest of the stuff I'm going to put under class handouts and more. Right now I only have one thing there, if it'll come up. It doesn't seem like it wants to come up. Okay, I've got the research paper instructions there, and we went over those last time. I think everything was correct, so I put that there. Now, as soon as I have the chance, I'll put your those links, websites, or whatever, the Hubble pictures from Hubble Space Telescope, the linked space objects in perspective, any of the other stuff I'll have like that. I'll put your PowerPoint shows here, static form, and then I'll have the link to the YouTube videos. That's usually the last thing there. So this will be pretty full. That's the class handouts and more. So syllabus, locator card, everything else. Make sense? Does this look about like yours does? Okay, good. Because I don't ever see it in a student side, so I'm not absolutely certain that's how it looks, but it's how it should look. All right. Any other questions in Blackboard before I get out of it? Okay. So, no reason to hang around there. All right. Now we're ready to start. And we'll start from current slide. All right. You said no questions from last time. Well, if you remember, we had been going through various things about stars, and one of the things we addressed was magnitude of stars. We first looked at apparent magnitude, which of course the closest stars look the brightest, like the sun, things like that. Let me get your name, please. Second. Ishmael. Okay. All right. Well, before I get going too far on this, here's what my plan is for today. I'm pretty sure, I think, knock on wood, that we should be able to finish chapter 14 today, the lecture part, what they call it, theory part. If we do, and that's before 3:45, then we'll go on and start chapter 15, okay? But it's right at 3:45. At 3:45, we'll stop, and that's when we'll start the lab. I have them made up, and we'll be right here in the room. We're going to do the lab as a whole class together as a lab, okay? And then hopefully we'll finish that in the 2 hours till 5:45. It is probably the longest lab we're going to have all term. So if it does go over, we'll just stop at 5:45, and then the first few minutes of Tuesday's class will wrap up the lab. Now, if we don't finish chapter 14 today, we will keep going until we do. If that takes us past 3:45, we'll pick up on 15 and just keep going on 15, and then Tuesday have the lab. Because I want to give you at least 2 hours to do that lab, because it's a long one. Well, actually, I'll do it at 2:45. 3:15, because then we'll, on Tuesday, if we finish chapter 14 today, which I think we will, whichever time it is, the test on 14 will be Tuesday, last 30 minutes of class on Tuesday. Okay, that's 5:15. Okay, and if any of you need extra time, I'll be here as late as I need to be. Okay, all right. Now, let's get back to where we were here. Any questions on that? So let's see if we can finish 14 before 3:45. I think we can. So, remember we were doing magnitude. We first did apparent magnitude, how bright they look, but that depends a lot on how close they are. Okay? Then we did absolute magnitude, that if everything was equal distance away, what would be the apparent brightness? Okay? And these are these scales. Remember, they're sort of strange little scales. Brighter stars are up here with the minus numbers, and dimmer stars are down here with the positive numbers. Okay? Now, then we jumped a rabbit, it seemed like, and moved to temperature of stars. You might say, why were we doing that? Well, those temperature scales were temperature in K, that's the Kelvin scale. Okay, the hottest stars are here, the coolest stars back that way. Okay? And we didn't give necessarily those numbers, though we talked about the numbers. These were the classifications. The O stars are the very hottest, and why it's O5, I don't know. Then the rest of them are followed by zeros, and that one's followed by an 8. Okay? So O5 is here, then B0, A0, F0, G0, K0, M0, and then M8. And they didn't give any explanation of why these two have numbers other than 0, because in the book they just said O, B, A, F, G, K, M, N, M. I mean, just one M. Okay. This is why we did absolute magnitude. This is why we did temperature and these scales. Because these two characters, a guy named Hertzsprung and one named Russell. I know Russell, I'm pretty sure, was American. I can't remember if Hertzsprung was American or German or somewhere like that. But anyway, it's probably in your book. Let's see if I can find that. No, Denmark. Henry Russell of the U.S. and Einar Hertzsprung of Denmark independently developed this scheme. So it's called the Hertzsprung-Russell diagram. What this does, if you plot the stars, start with a blank piece of paper with these scales on it, and you start plotting stars. The stars that fall in this sort of eel-looking band in the middle, those are called the main sequence stars. Those are just stars in their normal life. Okay? Now, after they were protostars, then while they're just good old regular stars. Some of these are very hot, and some are very cold. Some are very high absolute magnitude, some are very, very dim in their absolute magnitude. And that pretty much follows by their temperature, okay? Spectral type, okay? Now, when these stars start dying, they start going through a stage, okay? And one of the early stages here, and we're going to talk about this in the rest of the chapter. I'm just going to give you a little preview here. One of the early stages is, after a lot of stuff, we'll talk about what goes on, but they start using up their fuel, okay? And then they collapse on themselves, and if they're big and hot enough, then they start using more fuel, different fuel. And then they do that, and at some point, though, they blow up. Okay. Now, in the process of that, they're collapsing and getting big, and collapsing and getting big, okay, before that last nova or supernova. That big scale, phase that they're in, that's when they become the giants. Okay, that's normal stars. Okay, they're often called red giants, and these are typically cooler in temperature because can't support as much nuclear reaction, but they're fairly easy to see. They're high magnitude. Well, the high magnitude is how big they are, okay? And cooler, that makes them, a lot of these red. So those are often called the red giants, okay? Now, if it was a super duper big star, very massive star, very hot, they become the supergiants, okay? And they range from extraordinarily hot to very, very cool. These would be red. These wouldn't necessarily be red, but they're very, very visible. In fact, these are some of your biggest and brightest and most easily identified stars, because some of them are really hot and all of them are really big, okay? Now, when they finally pass through their last stage, either here or here, then they collapse on themselves and become the white dwarfs. White because they're still incredibly hot, and it takes them long periods of time to cool off, okay? So they'll be a white dwarf for quite a while, and that's why they're white, but dwarf because they've collapse on themselves and are very, very small. So therefore, they're not easy to see. They're so small. And their lights are generally fading. And after a while, you don't even see them anymore. They can range from very hot to pretty cool. But they went through the stage. Now, so keep this in mind. In fact, we will follow stars, but we won't have this diagram to point them out. Now, where are we? Where's our sun? It's right in the middle, okay? About average temperatures and average absolute magnitude. Of course, apparent magnitude is the big brightest, but apparent magnitude right in the middle, okay? Very, very close to the middle in just about every way. All right, now they mention a few stars here. Does anyone remember what the brightest star in the sky is? Are you
talking about the sun?
Okay.
Or the sun?
No, okay, not the sun.
So no,
nighttime stars.
Other stars.
Say again?
The no star?
No, it's a dim star.
No.
Say again? Sirius. Are you serious? Okay, yes, you are. Okay, Sirius. Okay. Actually, Sirius is one of and this is pretty common, a binary star. Part of Sirius is, and here it is in the main sequence, just tooling along, Sirius A. It's fairly hot, hotter than the sun, and absolute magnitude greater than the sun. Okay? The thing is, it's fairly close to us, and that's why it's the brightest one we see. But notice down here, there's a Sirius B. Okay? What that is because Sirius is a binary star. One of them's in the main sequence, the other one's on its way out. It's a white dwarf, and they revolve around each other. Okay? So you'll see several of them like that. Here's Procyon A, and there's Procyon B. Now, they don't always have to be one main sequence and one white dwarf, but a variety of them like that. Those are the only two I see on this one, but it just shows that they can be in that kind of pattern. All right. So the plot of these absolute magnitude versus stellar temperature, what Hertzsprung and Russell did was plotted each star by their temperatures and by their apparent magnitude, and then they grouped them. They saw a bunch of them act like this, and they seem to be similar to each other. Some like this, some like that, some like this. Okay. So purple is the main sequence stars, red giants are the blue, the novas, I guess is what they're calling the super giants, the white dwarfs down here, and now they throw in this, and it is not anywhere on there that I've ever been able to figure out why they put it on this slide. But these are the Cepheid, I don't know precisely how you pronounce that, Cepheid or Cepheid variable stars. These are sort of special, and I'm just going to read from the book. Hopefully you'll get your books one of these days. This is on page 361 if you have this edition of the book. Stars such as the sun emit a steady light because the force of gravitational contraction is balanced by the outward flow of energy. However, not all stars are constant like that. Variable stars, on the other hand, are stars that change in brightness over a period of time. And these Cepheid or Cepheid variable stars is a slowly changing variable star, and they use these to measure distances. What? Okay. There is a general relationship between the period and the brightness. The longer the time is needed for one pulse, the greater the overall energy output of that star. Okay? The period brightness relationship to distance is calibrated, comparing the apparent brightness with the absolute magnitude, true brightness, of a Cepheid star at a known distance with a known period. To me, blah, blah, blah. They do a very poor job defining that. Here they just put the thing up here, but they do mention a character. I've mentioned him before. Edwin Hubble. He's the one that figured out how to use these to determine distances. And it must be pretty complicated because this guy seems like he's tripping all over himself trying to explain it. And to me, I don't think I've read a paragraph that's more vague than this one is. Okay? But anyway, it is something Hubble came up with, and they use them all the time to estimate distances. Okay? I wish it described it better. The last edition said less than this, and at least it wasn't as confusing. But this says a little bit more, and it doesn't make it any clearer whatsoever. All right. Now, keep this in mind. You're going to see this diagram again, but without the color in it, and with just very few stars in it. So let's look at the life of a star. This is top of the second column on page 361. There was a little blurb here, science sketch. It says, sketch the brightness versus time graph illustrating the changing. Yeah, right. This is confusing as the last paragraph was, so skip that. All right, life of a star. We've already talked about parts of this. Remember, we talked about the masses of gases and some sort of a perturbation, what do they call it, pulse or something came through and forced some of those gas molecules closer to each other. They got attracted to one another. They closed in on themselves. They built up gravity, pulled in more. That was a gravitational collapse. And that's where we're starting. The protostar, once it got enough mass together and you had this gravitational collapse, in that, the density increases like crazy. The temperature increases like crazy. You get more and more molecules closer together, they heat up, like rubbing your hands together. The friction heats them up. The pressure increases, that's force per unit area. Everything is increasing. Remember the protostar? That's when it reaches the point of no turning back. Now it's going to become a star. Okay? The nebula out there that may or may not become a star. Okay? It's just a mass of gases. But when that collapse begins and gets to a certain point, then it becomes a protostar. Okay? Now, what is that point? Something around 10 million K temperature. Whoa, that's hot. Okay? That's where fusion begins. Hydrogen begins fusing to helium. Because before that, it's not going to be a star. Or it's not a star. There is no nuclear reaction going on. Once it reaches that 10 million K, then fusion can start. Okay? And when it does, all kinds of things break loose. Okay? Now here's what happened. Remember, up to this time, it's collapsing. It's collapsing. It's collapsing. The pressure's increasing. The temperature's increasing. The density is increasing. Everything's increasing there. And get hotter and hotter and hotter. So things getting smaller, and And all these things are increasing, okay, until nuclear reaction. Nuclear reactions happen. Now they're trying to blow up and force things out. This creates what they call a dynamical equilibrium. Now, this is almost contradictory, okay? Equilibrium means things are balanced. Dynamical means things are changing, okay? And that's what's happening. You've changed your parameters. You got nuclear reactions going on here, and that's trying to blow things up, but gravity's trying to pull it inward. That's the dynamical equilibrium. The inward force of gravity, the outward pressure of the fusion energy. Now, they don't go into great detail because I don't think we know great detail, and probably would be very difficult to do in a book of this nature. But in my mind, it's sort of pulsing. It's sort of going, you know, they're trying to figure out at what level it's going to sort of settle out. Okay? So there could be things spewing out of there and things being pulled in. You know, who knows? Okay? The reason I say that, in the next chapter we'll talk about the effects of some of that. All right? But when that dynamical equilibrium is established, then the star is a star. No longer a protostar, now a star, and it's in the main sequence. It started its real life as a star, and it will hang around for billions of years, trillions of years, millions of years as a main sequence star. All right. This is an illustration of this to some extent. Okay? Where does a nuclear reaction occur? At the core. Always in the core. Everything else is other stuff, okay? The core is where the nuclear reaction is going. That's what's gotten up to 10 million or greater K temperature. And this was basically your radiation zone moving outward. But then here's your convective zones here as gravity is pulling things in. And you have all this dynamical equilibrium going on. The inward force of gravity keeping things together. Outward force of those nuclear reactions in the core pushing things out. That's the star. And that's how a star lives. Constantly nuclear reactions blowing up in the core, gravity pulling things back in. Okay? Now, what happens to that star? They call it the star evolution. It traces a path across the Hertzsprung-Russell diagram. I want to say human relation diagram. It's not. This is Hertzsprung-Russell. Okay? Now, where did we leave it? Back here, main sequence. And it stays there, like I say, millions, billions, trillions of years. Okay? So it's in there for a long time. At some point, though, the hydrogen in the core is exhausted. Okay? Remember we said the sun has used about half of its hydrogen up. Okay? So it's about halfway through its normal life. Okay? Now, when that does occur, the hydrogen is used up, guess what? No more nuclear fusion blowing out. So what happens now? Gravity takes over. Dynamical equilibrium is lost. Gravity takes over and collapses into the core. I mean, everything into the core. Now, guess what that does? All that pressure, temperature, and everything heats it up like crazy. Okay. Now, there are a little, especially on the slide set here, and I'm going to say this in every chapter, especially at the end of the chapter. I'm going to say it now. Nothing replaces reading the book. So if you haven't gotten your books yet, please get your books, because I can stand up here and talk all day long. You can read these slides, and they leave out so much. Read the book. It fills in a lot of details here. I just don't have time to do it all. Okay? So, the core collapses. Okay? Remember, you have the outer shell out here. The core is collapsing, but the outer shell is now kind of expanding. Okay? Now, they don't tell you exactly why, but that's what's happening. So what does the star do? The core is getting hotter, the shell's getting cooler. Okay? But it's getting bigger. That's why it gets cooler. So it cools down from being a blue star, a white star, a yellow star, a orange star, whatever. It cools down and becomes a red star. Okay? But it's a big red star, and that's why they call it the red giant star. Now, they mentioned two of the classifications here. What are the O stars? Hottest stars. Hottest stars. Okay? They only last millions of years. And by the way, if they're hottest, they're the biggest. I'm not saying bigger than the red giant, but they have the most mass to them. Okay? And they only last millions of years because they get so hot they're burning it so fast. Now, I say burning it because they use this thing, but it really is fusing it so fast. The M stars are the least massive stars, and because they don't have that much, they're not burning it that fast, so they hang around for trillions of years. Where are we? In the middle, so guess what we are? What's in between millions and trillions? Billions. Our sun's about 10 billion year lifetime. It's been through about 5 billion of those. Only has about 5 billion left. But I think I'll make it before. All right. The mass determines the ultimate fate of the star. Okay? We have it going to red giant. What happens from this point on determines the ultimate fate of the star. So we'll talk about that in just a minute. So what is described here, it started out in the main sequence, okay, and then when it ran out of fuel, okay, and the fusion ceased, the core collapses, the outer shell expands, it becomes a red giant. And it may hang around at various stages in the red giant, and depending on the size, and this is not very specific here, but at the very end, it moves down this way. Okay? Now, we've only talked about this part. Don't worry about that part yet because we haven't gotten there. Okay? So, the hotter stars this way, cooler stars that way, absolute magnitude that way, high that way, low this way. Okay? Now, that picture's still in mind. Here's what happens at the end, depending on the size, how massive the stars are. Okay? Late in the red giant stage, these are the smaller stars, the least massive stars. Okay? The core continues to collapse and heat. Now, what's in the core? Remember, we used up all our hydrogen. What's in the core?
I know the very last step is when it produces iron, and that's the death of the star. But
Okay.
I don't know what happens right before. I know it's hydrogen and all them other little elements. But
Okay, what's right after hydrogen? Anyone remember? Huh? What you say?
Oh, I had guessed the wrong thing.
Okay.
And I doubt the oxygen would
No,
be
no.
left over there.
Helium. Helium. Hydrogen's the lightest star, lightest element. Number 2 is helium. 2 hydrogen fused to make a helium. So now you have a bunch of helium in the core. But the core is collapsing. It's collapsing and getting hotter and hotter and hotter. Now, they don't give a temperature here, but it typically happens that it gets so hot that now the helium fuses and it fuses to carbon. Okay? So the hydrogen fused to helium, and then late in the red giant stage, as the core is continuing to collapse on itself, it's hotter and hotter and hotter. Finally, you reach that ignition temperature for helium to start fusing, and it becomes carbon. Okay? Now that's hot. That is really, really hot. Okay? Now, the radius and the luminosity decrease. Okay? And they're very vague on why. I can't figure out why the radius decreases. It seems like to me now it should be expanding. But remember in the red giant stage, the outer core was expanding. Now it starts decreasing. So guess what? It goes back to being a main sequence star. Hotter star started down here, is up here now, and why? Because helium fusion is really, really hot. Okay? The radius decreases, so therefore your ability to see it decreases, and it moves back toward the main sequence. Now, it depends on how much helium is there. It will stay there as long as it's now fusing helium to carbon. It reaches a new dynamic equilibrium, and it goes from there. Now, that's late in the red giant stage. Now, that's all the stars. All stars do that. The least massive, the greatest massive goes into that. Okay, now, let's talk about the end. The end of the less massive stars, those are the lightest ones. The helium is used up. You know, you've used all the hydrogen and helium. Now you've used all the helium and carbon. Hydrogen fusion in a long while ago. Helium fusion now. Okay. Nothing left. Now the instabilities blow off the outer shell. Remember the outer shell was out there. It blows it into space. Okay? And that's what forms the planetary nebula. Now, this has nothing to do with planets, except for the fact that the core is here and the gases are out here, just like the sun's here and the planets are around. That's why they say planetary nebula. If you remember the picture early in the chapter of a little, I said, that's a little white dwarf in there, and there's the cloud of gases that's blowing up. This is right near the end of this slide. That's what a planetary nebula is. That's where the small, low-mass stars actually happen. They blow up, blow off, and it takes a long time. I mean, probably hundreds, thousands, maybe even, I don't know if it's millions of years for that shell to, just diffuse into space. What's left over is the white dwarf. The carbon core contracts to, notice there, every time the core is contracting, the shell is blowing out. Okay? Again, it's doing that. Contracting to a white dwarf. Okay, now why is it white? It's so hot, because it's contracting. Now, no more fusion going on. So it's all friction heat, but it still gets hotter. So it's the white dwarf in the middle, planetary nebula, the gases outside of that. Over time, because there's no more fusion, over time it just cools. Okay? So it goes from being a white dwarf to a black lump of carbon. And because of that white dwarf, remember, very high temperatures, enormous pressures, carbon, Lucy in the sky. Okay, that's where that came from. Okay, so that's your least massive star. Okay, let's see if they got another slide here. Yeah, there's that planetary nebula again. The white dwarf in the middle, and that was its cloud of gases blowing up around. Why it's called planetary? Sort of like the sun in the middle and the planets around it. Okay? So these are not planets. That's the outer shell of gas blowing up and going into space. Pretty sure that's another Hubble Space Telescope picture. And by the way, I think Hubble has actually outlived what they thought it would, but it's still sending some pretty good pictures back. But it's on the end of its lifetime. I think there are plans afoot, and they may have even started, to building a bigger and better and more incredible telescope, and who knows what we're going to learn then. I don't know where they are in that process, though. Second? No, it's just out in space. It's sort of like a satellite itself, yeah, going around the Earth, yeah. But it's far enough out so you don't have any atmospheric interference. Okay, now. What's that? Yeah. The first one was called, started with an M. Mariner? I think it was. No, those are the ones that went to Mars. No, Voyager. It didn't start with them. I was thinking Mary. Voyager. Voyager, they sent out a long time ago. That old thing is still just going. I don't know if we can hear the signals anymore because it just got so faint. It seemed like it was just still working. Actually, one of the Star Trek movies, I don't know, not Star Wars movies, Star Trek movies, I think the first one somehow used Voyager in it, and it was V'ger is what it was called there because it had collided with something else, and it was science fiction, but it was interesting they did use that. And I'm sure there are others that are just going and going and going. Okay, so let's go to the more massive stars, okay? The massive stars. Those are the sort of little stars. I don't know where the Earth falls in this, if we're little star or the middle massive. I think we're still on the little side. So let's go to the slightly more massive stars. More gravitational contraction and heating, okay? Now, they tell you this, okay, here they do. Remember, 10 million K was where hydrogen fused to helium. That's when you start the nuclear reaction. When you reach 60 million K, that's where carbon fusion starts. And we had that on the last slide. I didn't remember what the temperature was. 600 million K, okay, way high.
The last slide that you were talking about, there was you had it at 100 million K. Now on this one went up about 500 million.
Okay, the other one was 10 million K, and this is 600 million K, yeah. So it went up by 60 times. Whoa, okay, that's high. Now you said carbon fusion. Now, not only carbon fusion, but some of the heavier nuclei begin to fuse. And this is what you were talking about. As it gets hotter and hotter and hotter, more fusion happens. Actually, carbon fuses to something heavier and to something heavier, and ultimately it'll go up to iron. And at that point,
It's doomed.
Second?
It's doomed. If it reach iron, the
What
star
about it?
is doomed.
It's doomed.
Doomed.
Okay, sort of. Okay, hang on to that. That is as much as it will happen spontaneously, as will happen in a natural kind of pattern, up to iron fusion. After that, it won't fuse anymore. Okay, naturally. Now, the energy expansion pressure is lost. So when you finally use up and everything's gone to iron, there's nothing else to push out. The dynamical equilibrium is disrupted. Now it collapses.
When on the core.
Yes, the star collapses on itself. No more dynamical equilibrium. No more nuclear reaction. You got up to iron and nothing else is going to form, and it collapses. Okay, and when it collapses, huge is that collapse. I mean, you're talking enormous amounts of energy there. And because of that collapse, the temperature is way up, the pressures are way up. Now, what wouldn't happen irreversibly down here happens now. Elements beyond iron are now created when they collapse on themselves. It's sort of like, remember, that's how I described the nuclear reactions. You have two, what they call, in the regular fission reaction, two hemispheres that are almost with critical mass. You force them together. Actually, they blow up conventional bombs, forcing them together, and that then creates a nuclear explosion. Okay? This was all theory until we did it over Hiroshima. Okay? They were our experiment. And we tried it again to see if it worked in Nagasaki with different elements, and it did. One was uranium, one was plutonium. Shame to use cities of millions of people as your experimental thing, but that's what we did. Okay? And then when we went to make a hydrogen bomb, you had the conventional bombs forcing together to make fission, then you had several fissions forcing together to make the fusion. Okay, well, that's sort of the same thing here. Hydrogen fusion, the collapsing makes other things. Next steps in the fusion, and that's when the heavier elements happen. If it wasn't for, if that didn't happen, iron would be the heaviest element we had, because that's the only one it goes to normally. But because of that enormous collapse and rebound, that's where your other elements are formed. But what is and we'll learn this in the next chapter, so I should get ahead of myself. But remember that. Iron is what it goes to naturally, sort of an irreversible reaction. I don't know how to say that. This happens in the extreme cases. Now, so these are the more massive stars. It goes through this. The less massive stars, they wound up just after carbon, helium fusion to carbon, they've spent all their energy. They don't have enough to get hot enough to do the others. The more massive stars get hotter, carbon fuses to iron, and now you have this other stuff going on. These are called supernovas. Now, what happens after the supernova depends on how big the masses are again. Okay? So let's go to the next slide, which goes, what's that? Oh, I'm sorry. I thought I was yakking so long that y'all had time. Okay, I don't mind at all.
How do they know that this stuff happens?
What's that?
How do they know what's in the stars? Like, how do you know what carbon's in the stars?
Okay, good question. If you look at a star with your eyes, it just looks like any other star pretty much. Occasionally we'll see slightly different colors and things like that. But if you look at a star using specialized equipment, you can study a star looking at the X-ray patterns. You can study it looking at infrared patterns. You can study it looking at different energy spectra and stuff like this. And when they look at it, dividing out the energies, every element emits a characteristic set of spectral lines. So they look at the spectral lines and they divide out, these belong here, these here, these here, so they can determine what's there. It's really a neat process. It's the field of spectroscopy. Okay, I think it's probably where you find that if you want to look into that a little bit more. Yes?
Wouldn't like the Big Bang be considered a supernova?
Okay, all right, my hearing to that.
Would the Big Bang be considered like supernova?
What's that again? One more.
Would the Big Bang be considered like supernova?
That would be a supernova. Okay, or something like that. I mean, we've only had one of them we know about, so and we have these all the time. So all the time, but they're happening all over the place. So it would be, you'd have to have about 15 dupers to go with your super, to make. I'm making that up. Okay. But yeah, it's much bigger than these. Yeah. And guess what? It's still just a theory. No one was there. We can't repeat it. We can't say, let's see. If this happens, can we do it again? No. It's a theory. Okay. Everybody got it? All right.
So excited about the neutron stars.
What's that? Yes. So, this is only happening with the bigger stars. The others just became lumps of coal. Okay. So, how about the more massive stars? When that remaining core, after everything else is spent, that remaining core is still like 1.4 to 3 times what our sun is normally. So, the whole sun. Then the gravitational pressure of that last collapse, okay, not enough temperature is produced to do any more fusion, but the pressure is enormous, and it forces all of the electrons to crunch into the protons and become neutron stars. Okay?
And it got the same mass as where it was, just more denser.
So this
I say it got the same mass that it was, but just more denser and more smaller.
Okay. If there is any loss of mass, that would be becoming energy. And I'm sure it's emitting some energy, so I bet you it does lose a little. But This may be what you're actually saying. That's why a neutron is just ever so slightly more massive than a proton, because it has an electron fused in with it. Okay, is that what you're asking? That's exactly right. Okay? So, you have protons, electrons fused in the neutrons. Now, let me explain what a neutron is. Okay, a proton is a positively charged nuclear particle. A neutron is a neutral, no charge nuclear particle. An electron is this tiny, tiny little thing that floats around, and it's a negative charge. Okay? So when you put all that together, protons being positively charged, they tend to repel each other, right? Okay, but a nucleus is still really, really dense. So there's some, they call it the strong nuclear force holds that together as a nucleus. So the protons are trying to push each other out. Okay? Neutrons are just hanging around. They don't do anything. Electrons take up this huge cloud around there, and that's what most of our atom is that electron cloud. Well, guess what? There's nothing there but space in between these tiny little electrons. And that's why my older brother's physics teacher, when he came home sometime in sophomore year, he was so excited. He said, "Most of everything is nothing," you know, and that's because what occupies most of the space of an atom, the heaviest, densest atom out there, lead, osmium, whatever, most of what occupies that is space, nothing in it, because it's an electron cloud. All the mass is concentrated in that little bitty nucleus, okay? Little, tiny little nucleus. But that's got protons and neutrons in it. The protons are pushing each other apart. Neutrons are just hanging in there, okay? Now, when the electrons are pushed in to become with the protons, and now everything's neutrons, there's no force outward. So they get just as close as they want to get. No cloud of electrons anymore. Tiny, okay? So when you're talking about a neutron star, you're talking about one dense bit of matter. I mean, it's about as dense as you can get. Now, I don't think they do a great job of explaining this, but there have to be some charges left over. The reason I say that, and maybe not in every neutron star, but in some there must be, because they have discovered these pulsars. Okay? Now what that means is a pulsing star. Pulsar. It rotates, because all of them are usually spinning, but they have strong magnetic fields. Okay? So you have a rotating magnetic neutron star there, and when a magnetic field is produced by moving charges. That's why I say you have to have some residual charge somewhere there, and that then makes a pulse. Because if it's spinning and also going like precessing, then it's sending out varying magnetic fields. And if it's a varying magnetic field, it's pulsing. And you can find those. At the end of the chapter, you're going to read about, if you choose to do so, a woman named Jocelyn Susan Bell, or I mean, she has several names.
I'll let you finish.
What's that?
I said the reason why it's still so powerful with the magnetic field is because the core is still like the rotation rate is increasing real fast.
Yes.
That's why it's still very powerful, even
yes.
though it's very small.
Exactly. And it's small because it's all collapsed on itself. There's no, but like you said, it's rotating rapidly, and a moving charge produces a magnetic field. That's the first half of the book, in magnetism. You can go back and study that. And that makes a very strong magnetic field because it's so very tiny.
And per second.
And what?
Per second. Like it spins very fast.
Yes.
Like per second. Like how light go fast
yeah.
per second. It goes twice as fast per second.
Oh, I see. The speed is very, very fast. And that's what creates the pulse. Because it's also recessing and you're getting different signals from it. Now, what I was going to say about Susan Bell Burrell, whatever her name all is, she was the first, or she was working at a lab, a telescopic observatory, space observatory, and in working there, she noticed this pulse out there that she couldn't account for. And she checked all her instrumentation and stuff, and she kept tracking it, following. She was very persistent, and ultimately identified it as the first identified pulsar anyone had ever seen. Okay? Now, I think I've got my story right here. I know this happened to at least one. I think she was one of the ones that happened to. That normally would have been enough for a Nobel Prize in Physics. But you see, she hadn't gotten her PhD yet. She was just working at the lab underneath somebody else, and that somebody else with the PhD, because he was the honcho, he got the Nobel Prize. And he griped and complained and said she should be a co-laureate with him. Okay, I know I have to take it, but she should be with. No, she doesn't have a PhD yet. It was basically sexist discrimination. Call it what you like, that's what it was. The good old boys did not give you a Nobel to a woman. They have subsequently, but Marie Curie, I think it was before her, she got one. Because nobody could argue with that, but they still didn't like it. Sorry about that. That's a little political, but it's reality. Sorry. Now, so that's what happens with very massive stars. Stars between 1.4 and 3 solar masses left in the core. Now, that's not their whole mass. That's just in the core. The black holes, though, is the resulting, the end game for those stars that had cores greater than 3 of our solar masses. Just, we're using the solar mass because we sort of know what that is. When you got more than that, boy, you're talking an enormous amount of that. Now the gravitational collapse overwhelms everything. And we don't know what happens. It's not neutrons. There's too much collapse for that. It overwhelms all known forces. Okay? Now, a neutron star can send out electromagnetic energy, the pulses. Black hole doesn't. Nothing escapes. Electromagnetic radiation, try to leave, suck back in. Overcomes every force known to anybody. And no one knows what happens. There's some theories, yes.
Black holes don't like die out or nothing.
No, they last a long time.
Say this again.
Like black holes don't die out or nothing.
Okay. Now that's a very interesting question, and I'm not sure anyone knows the answer of that either. There's a bunch of theories out there, and some of them make various amounts of sense, yes.
Our galaxy has a black hole.
Oh, yeah.
Them, so they really can't die out because there's like a really old black hole.
Okay. There are so many theories out there, they make it seem like science fiction all over again. Mm-hmm. There are some theories that say the energy and the mass that's being sucked in is going into a parallel universe and now is being emitted, in that other universe. No, I can't wrap my head around that one. And others, and my older brother reads this kind of stuff all the time, and he called me up one night and asked me, he said, okay, and it was a question very much like yours. If this is happening, why aren't they getting more massive? But they're not, okay? That they know of, but they're sucking stuff in. Where is it going? Nobody knows. We don't know where the exhaust is for a black hole. We don't know what's happening. We don't know things about black holes. We have theories about them, and that's why your paper topic can be really overwhelming if you don't watch it, because there's so many theories. So narrow it down, focus on one set of theories there. But we do know that's why they're black. No light escapes. No magnetic radiation escapes. Nothing escapes. So
even other black holes don't escape.
Yeah, I mean it's sucking in anything that gets close to it, and
it expands the rest out.
What's that?
it expands the rest out like two streaks of energy come out the black hole. If it has like a whole lot of mass to it, it expands jets like gamma rays.
Okay, so it is losing some energy somewhere.
When it gets too much,
it
expands it.
Okay. Okay, no, there's no way to see that. That's what I was trying to say. Okay, excellent question. Now, that's what I was going to get to. You see things because they're emitting things. Whether it's light, then you really see it. If it's electromagnetic radiation like a neutron star, you can detect that. The spectral lines we were talking about before, you can detect those. You can detect something. The black hole is, we just know that everything's...
You will know because it'd be like one dark spot around a whole bunch of energy.
Didn't we talk a little bit about the next two planets they think are out there? They haven't seen them yet, but we see effects of them. We see gravitational effects and other things, so we know something's got to be out there. Well, that's it with a black hole. Like we said, our galaxy and every galaxy is centered around a black hole. In fact, there are galactic clusters, smaller pieces of the galaxy that have little black holes, and everything's doing around that. So we know they're there because of the effects they're having on other matter. Like our galaxy, nothing could make all these billions of stars roll around like this unless there was something in the middle sucking them in. I mean, just like, why do we go around the sun? Because the sun's gravitational field is pulling us toward it. Otherwise, we'd just be flying off into space, and we wouldn't exist. Well, same thing with the galaxy. Something has to be keeping all those stars going around it. So it has to be enormously massive. But we still haven't seen one. We see the results of it, but we don't see it. We can't measure anything coming out of it because very little escapes. Okay? And that's why it's open to science fiction, people guessing what could be done. It's a fascinating topic. Okay? And other things. Stars going around it. You see the star, you see the star, you see no star. You see no star, you see the star, you see the star. It's not in a shadow, it's that no light went through that black hole because when it tried to, it got sucked in. So, there's things like that. You see the effect of it. Same way, and that's sort of equivalent to these stars out there, and you, if they're studying the star, focusing the spectral and other things on that star, and then a planet moves in front of it, it changes the spectrum. And therefore, hey, there is a planet there. And we can guess how big it is and that kind of stuff. Okay, same thing here, except it's in reverse. It's like the negative of that. You see the star, you see it disappears. It shows up again. It shows up again. Something was blocking it from the, so it's incredible. Okay, I'm just making a little of this up, but this is my understanding of it. All right, so here is a summary of this. In your book, this looks a little bit better. I like the diagram in your book a little bit better than this. There is, and by the way, I'm pretty sure one of the Hubble Space Telescope pictures is very similar to this cat's eye nebula that you see here in the text on page 363. But here is the lifetime of a star. Yours is a little prettier than this one. This is an old slide, okay? You have that massive gaseous nebula just floating around out there. Enormous, really huge in size. And something makes it collapse on itself. Some pulse, something happens, and it collapses, and when it does, then it pulls more molecules in and more. So actually, if this were to scale, this would take up several rooms of wall. This would take up that space. It's really a huge collapse. When it collapses enough to get hot enough to start fusion, that becomes a protostar. That's going to become a star. A nebula will not necessarily become a star. It has potential for it, but before It may become something like a protostar, but when it reaches a protostar, can't go back again, it's going to be a star. Okay? Then it becomes a main sequence star. It could be a little one, a big one, whatever. Okay, main sequence. The low mass stars, when they finally use up all the hydrogen fused to helium, they collapse on themselves, use it all up, the core collapses, the shell expands, and they become red giants. Okay? And at some point, then, if the core gets hot enough, hydrogen fuses helium fuses carbon, and when that happens, it doesn't take as long for that to happen. When it spins that, then it blows up again, and what's left over is a white dwarf, and probably a massive gases around it, which is a planetary nebula. Well, they showed it up here. And the core was a white dwarf, and it wound up, and all that was left was carbon. Now, what form is that carbon? Could it be diamond? Seems like some of it would be, but we don't know. Okay.
You
Yeah.
have to like get the world out of space.
Yeah.
Is that not a thing?
Well, yeah, but there's a lot of space out there, and the lumps we don't know. Okay. Now later in this chapter is another chapter. We're going to talk about. Yeah, it's later in this chapter. Dark matter. You don't see these because there's no light coming out of them. There's no electromagnetic radiation. We don't know how many of these are out there, but we know there's a lot of them out there. And this is sometimes called dark matter. Dark because we have no way of telling it except sort of gravitational effects, just like before. So that's, to me, is part of what dark matter is. Now, the mid-mass stars, okay, they go to a red giant. Notice these are bigger red giants, okay, and one of their collapses, you really see the planetary nebula. There's got to be one here too, but it's not as pronounced. Planetary nebula. Finally, it becomes a white. The gases are blown off. The core becomes a white dwarf, and it goes just to being a cold lump of carbon. But the high mass stars, the really high mass stars, huge red giants, when they first have their use up their hydrogen and blow up, and then they collapse. It's not just some little planetary nebula. When they collapse on themselves, they're fusing. They go through several stages. Carbon fused to iron, still in this stage, and then when they really collapse and go up, the heavier elements are created. And now this aggravates me in both of these charts. You're more massive, more massive, more massive, but here they have the less massive before they have the more. To me, the neutron star should be here and the black hole here, because that's the most massive. Neutron star is the less most massive, So I don't know why they did them backwards in both cases. To me, the black hole should be the ultimate on the mass side, but they didn't. So between 1.4 and 3 Earth's masses left in the core becomes a neutron star. Anything greater than 3 becomes black holes.
If a neutron star was not like what it is, it could basically be a black hole because it does the same thing. Anything that it gets near, it rips apart and it clashes on the neutron star. As with black hole, it just eats it. So
except neutron stars emit electromagnetic radiation. Black holes don't. That's the difference. Things do escape from a neutron star. Nothing escapes from a black hole. Except on the sun.
Thing is kind of similar.
Yeah, they're very, very enormously massive, unbelievably massive. I think I've heard the illustration. If we had one little grain of sand, if that was a neutron,
it would destroy this Earth still.
Yeah, it would be more massive than the Earth is. It's just the scale is just unbelievable, unbelievable. I don't know if that's completely accurate, but I've heard something like that said before. Okay. That got us through the stars. And let's see. There's a closer look at the top of page 364, observing with new technology. And this is sort of what I was referring to before. there's different ways of looking at things. And here they mention several kinds of devices. Chandra, who works down in, no, a different one, uses X-ray, is an X-ray telescope, and it studies certain deals. There's another one mentioned here, XMM Newton X-ray telescope. Then they have infrared telescopes that measure heat being emitted. Gamma ray telescope telling you about gamma ray, that range of electromagnetic radiation. And by the way, here's one. This one was in the news in the last 5 years. The Arecibo Observatory. Anyone know where that was mentioned? Remember Hurricane, goodness, which one of them was it that hit Puerto Rico? Remember? Okay. Arecibo was the observatory on Puerto Rico. And that
Hurricane Maria.
Maria, that's it, Maria. You're absolutely right.
Yeah, it's been all over the news now for about a year now.
Oh yeah, longer than that probably. And the thing is, I think they've got Arecibo back up running again, but that was one of the biggest casualties, was that. Other things that were casualties that I never would have known about, except I've been on a synthetic hormone that's for thyroid. It's called Synthroid. And along about a few months after Maria went by, it said, your copay on your Synthroid, which is one of the most commonly prescribed drugs in the U.S., or maybe in the world. Because, at some point your thyroid doesn't produce as much as it used to, and they put you on this. And they say, your copay is going from $10 to $40. What? Why? Well, they manufactured these in Puerto Rico. The whole thing was wiped out. Now we're having to import them from Chile or somewhere else, and it's a lot more expensive from there. So Puerto Rico, they're bankrupt and everything else, but boy, we sure use them a lot, don't we? Okay, and then the a very large array that studies all sorts of different signals and stuff in New Mexico. Socorro County, New Mexico. Why do they choose these places? No light pollution. They're out in the middle of nowhere, long miles before anything else. There's a good picture of a pulsar there, an illustration of it. And then they talk about light pollution on page 365. And I think what you were referring to, the jet of particles that stream out of the center of a galaxy, powered by the monstrous black hole, estimated to have swallowed up matter equal to 2 billion times our sun's mass. And like you said, this is when it spews some of that out. Okay. And then the last figure there shows out in where there is no light pollution, a picture of the Milky Way, which leads us to larger scale structures. How are we doing on time?
It's 2:40.
It's what?
2:40. It's 2:40.
240.
2:40. Okay, so we've got
About
an
another
hour. I think we can finish it in an hour.
A whole hour.
Okay. Huh?
A whole hour.
Yeah. So the larger scale structures. I've already mentioned this first one. Believe it or not, a unitary star like our sun is very rare. Most of the stars out there are binary stars, not unitary stars. Okay, they occur in pairs. Two gravitationally bound stars that just go around each other. Most stars are binary stars, pairs, not ours. Now, all this talk about life on other planets somewhere else, some star far, far away? In my mind, my poor little mind here, I can't picture how a binary star could have planets that support life. Because at some time in that planet's evolution or annual trip around the stars, sometimes it's getting radiation from two stars, sometimes from one star, more than less. Sometimes we're in the shadow of one. And guess what? That would change your temperatures wildly. Okay? And how in the world could life adapt to those kind of extreme changes and radiations and other things? You have to be further out. I don't know how it works. Okay? I don't know how a binary star could have a habitable planet here. Around it. I may be wrong. I may be totally wrong, but I cannot see how it would. It seems like to have a planet like ours, you almost have to have a sun fairly similar to ours, okay? Because just a little bit of a variation, if you think about it, the tilt of our planet changes us from North Pole to equator. Think of the range from all ice to never ice, okay? And if anything was changed just a little bit, we wouldn't exist as we know ourselves. Okay. So we have binary systems. You also have clusters. They could be tens to hundreds of thousands or more gravitationally bound stars. And they say often those share some common origin. Now, I don't know when these star clusters, if that gravitational bonding of them is from just each other, or if it's from a small black hole. It seems like to me it could be either. Okay? They often say, okay. Then we have galaxies. Now, believe it or not, the basic unit of the universe is not a planet. We're pieces of dust. It's not a star. I would have thought that was the basic unit of the universe. No. Basic unit of the universe is a galaxy. Okay? And galaxies are billions and billions of gravitationally bound stars. Okay? But guess what? You have clusters of galaxies. Okay? Just like you have clusters of stars within a galaxy, you have clusters of galaxies. And then super clusters of galaxies. This is mind-boggling. And then on top of it all, we have, like, say, billions and billions of stars in one galaxy. We have billions and billions of galaxies out there. So when you look at what we are in perspective to what the universe is, we are less than a speck of dust, okay? Because the scale is enormous. Unbelievably enormous. Okay? Well, our little galaxy is the Milky Way. Now, have any of you ever been out on a dark night in wide open spaces where there aren't any lights around and you have actually seen the Milky Way? Okay. Yeah, I hope that sometime you can get out somewhere far enough away from the city that and it has to be a fairly clear night and with not much of a moon and see the thing. It's just this, it looks like someone spilled milk in that bowl. You know, the celestial sphere, someone spilled some milk inside the bowl, but it's upside down. So, it's visible as a diffuse band on a dark night. It has to be a really dark night to see it. Billions of stars, some bound in, I think they mean star clusters, because galactic star clusters are multiple galaxies. I think they mean star clusters. Okay? The structure is basically this. Every galaxy has some sort of or at least our Milky Way, has a galactic nucleus. Okay? Now, let's see if we can get a picture here. Okay, well, first, here's a nice picture of the Milky Way. This must be out in New Mexico or somewhere. You see, this is that diffuse band of stars. is so many stars in front and behind and next to each other that you can't make out the individual ones. I mean, there could be millions of stars in that little blob there, okay? They're just so close together and stuff that you can't do it. Now, don't worry about this. That could be aberrations of your thing. But that is the Milky Way, okay? I've never seen it that clearly, okay? But obviously, there's some places you can't see, okay? So that's one of the better pictures I've ever seen of it. Still, there's stars above and below it, okay? We'll talk about that later, too, okay? Now, here's the picture here. The galactic nucleus is a huge collection of stars. Now, this is looking from on top. The Milky Way, like our solar system, is sort of a plate, okay? Okay? Now, and like our solar system, there are things above and below it, but most everything is in that disk, that plate. And in the middle of that is your nucleus. That's the galactic nucleus. Looking from the side, if you took the plate here and turned it this way, then you see the nucleus here and the bands around it, and then just various stuff out there, okay? So this is the nucleus here. I don't know what it would be like to live in that nucleus. I mean, still the stars are so far away they're not interacting with each other, but there your sky would be just enormously bright at night, you know. Well, I don't know what a night would be. It just seems like that would be incredible. So we live out here, okay, about 2/3 of the way out from the galactic nucleus. So what we see of the Milky Way when we see it, we're either looking back this way or we're looking up this way, okay? And you see just nothing but masses of stars there. When you see on either side of it, you're looking and seeing this. There's still stars out there, but not nearly as dense, okay? And here we are, about, I said, 2/3 of the way out from the nucleus. Okay. So, and this probably isn't showing all of them, but just imagine if that little dot there was the sun, look how many others are around there. So, okay. From this perspective, the Milky Way is what we're looking at when we look this way or that way. We don't see this band in here. We don't see that the galactic nucleus. We just see the stars on either side of us, one side or the other. Depends on which way where we are in our spinning and stuff that what we see. Okay? Unbelievable to imagine this. So there's our galactic nucleus. Then the rotating disk, and the diameter of this disk from one side to the other, from here to here approximately, about 100,000 light years. And remember how long, what does a light year measure? Second? Yeah, it's a huge number. What is it measuring? Distance? Huh? No, okay. It is measuring distance, not time. Just because it's called a light year, it's not a measure of time. It's a distance. How far light travels in a year? Traveling at 186,000 miles per second. How far does it travel in a year? It was something in the trillions. I don't remember. 900 trillion or something. I don't remember. Miles or kilometers or something. Okay. It's an enormous. This is 100,000 of those. Okay. So you're getting such big numbers I can't even imagine. So talk about interstellar trip to galaxies far, far away. No, you're not. You couldn't possibly get from one star to the other star. Not with our technology. It would take you lifetimes. Lifetimes to go to the next nearest star to go across. Hang on, Jack. Okay, no way. All right. Now, there are also spherical galactic halos. That's what this is. And when we do our solar system, you'll see something that looks a lot like this. Around it, this is the nucleus. There's the spirals, the disk, and then still around it you have these spherical galactic halos, containing about 150 globular clusters of other stars. Okay. And each of those could be tens of thousands to hundreds of thousands of stars. So it's probably that's what each one of those little dots are clusters, globular clusters, that don't show 150 of them, but you can imagine that. And then each one of them are tens to hundreds of thousands of stars. And just that, that's the sparse ones. These are the dense ones. Those are the very dense ones. I mean, kind of unbelievable, isn't it? Now, not only are there stars and galaxies, well, these other galaxies, our nearest neighbors, there's what they call a local group. And this is made up of some dwarf galaxies about 1,000 light years in diameter. Now remember, we're 100,000 light years in diameter. There's some dwarf galaxies there that are like 1% of our size. I'm talking Milky Way size. The nearest dwarf galaxy is being disrupted gravitationally by the Milky Way, which what I assume from that, it's whatever is trying to travel, it's being disrupted and probably going to be sucked into our galaxy and wind up as one of those clusters or added to a spiral or something, who knows. Now, let me go back a slide. Doesn't it look like these stars are awfully dense? It's almost like they could touch each other. No way. They're so far apart, so incredibly far apart. The two closest here, are incredibly far apart. They say that if two galaxies collided, they never touch. They just go through each other because there's so much more space in between the stars than there is within the stars. So they just go like that and just kind of like a ghost or something like that. Of course, I've never seen one happen. I don't think anyone has, but that's the theory. Okay? So, our next major galaxy is good old Andromeda. It's about 2 million light years away. Okay, remember we're 100,000 light years across. So to get to 2 million, you would have 20 of our diameters between us and the next galaxy. So if we're here, say we're here, then 1, 2, 3, 4, 20 of us, before you get to the next one. Okay. It's sort of hard to figure. Okay. Now, the Andromeda is very similar to the Milky Way. And we have seen pictures with the Hubble Space Telescope of Andromeda. So that's how we know, or we think we know how we look, because we look like that, And good old Edwin Hubble, there he is again, came up with a classification scheme of these various galaxies. And I don't have pictures of these, so I don't know exactly, I can't describe to you. But what an ellipse is like a circle that's been stretched in one dimension. Okay, that's an ellipse. And there are elliptical galaxies. Okay? For instance, our path around the sun is not circular, it's slightly elliptical. Ever so slightly. Different ones of the planets are more or less elliptical. Pluto is very elliptical. Comets are enormously elliptical. Okay? So these elliptical galaxies would be galaxies that, again, are sort of flat, but stretched out. Okay? Then we are a spiral galaxy. You saw the spirals from the galactic cluster. Then they have the barred galaxies. And I can only imagine what these are. They have spikes that go out. I don't know if it's all in one plane or if it's in all the planes. Probably in one plane. And then we have irregular ones. They're just out there, Now, my guess on this, they would have fairly weak black holes in the middle. I think we have a very big, strong black hole. Yes?
When you discover
Say this again? floating up in the sky. And later we found out, oh, that's our galaxy. Okay. I don't know when that realization occurred. I would guess, and this sounds weird, I would guess within no more than 3 or 4 generations ago. I think that all our understanding of this kind of stuff has been within a few generations, maybe 5 or 6 generations. I don't know. It hasn't been that long. Okay. And we called ours the Milky Way galaxy because that's what we had called that diffuse band of light across the sky at night. We called it the Milky Way. And later found out, oh, that's our galaxy. Okay. No one knew what it was before. Okay. So it's sort of like, I don't know. Someone discovers something and names it after themselves, and later they find out it's something totally different, but they keep the name. I don't know. Okay. There's a picture of Andromeda. Okay. Actually taken from the Hubble Space Telescope, I'm pretty sure. There's its galactic nucleus. And its bands are not quite so clear because you had to blow this picture up so much it lost it. But you can sort of see some bands, and it's not at a great angle to see it. But that's it. I actually think Andromeda is probably bigger than we are. I think I've read that somewhere. These must be some other galaxies somewhere far, far away beyond that, or at least galactic clusters or globs or something. Okay. Now, when we talked about the life of a star, what would be the life of a galaxy? And someone else was asking this question earlier. And folks, an awful lot of this is speculation, based on some pretty good science, but still speculation. This is a theory. We don't know if it really happened this way, but the Big Bang Theory says the universe evolved from some unbelievably hot, big explosion at the beginning. Now, what's the supporting evidence for that? Like I said, these are theory, but they do have good science behind them. They are still measuring and can continue to measure microwave background radiation, that the characteristics of this, as they go deeper and further away, it all indicates that something did explode. Okay? Now, good old Hubble again is responsible for finding out that there is and has been and continues to be large-scale expansion. Now, do any of you know what the Doppler effect is? Okay. Have you ever been sitting at a train track and the train's coming and starts blowing its whistle? Now, certainly it gets louder as it gets closer, but also the frequency goes up. But then when it leaves, it gets lower in frequency. Certainly the loudness you understand, but the frequency is also changing. From low frequency, high frequency, low frequency. That's because when it's coming toward you, the speed of sound is a certain speed, and the emitting the sound, that's the whistle on the train, is coming to you, so it's pushing the wavefronts closer together so the frequency goes up. And then when they leave, they're spreading out again. So it goes from low to high to low. Okay? Well, Hubble, I think it was, who said, look and light do the same thing. When something is coming near you, then the wavefronts of the light would be getting closer, so therefore the frequency would go up, and it would be shifting towards the blue end of the scale. But when it's going away from you, it would shift towards the red end of the scale because we're getting further apart. And he documented redshift. Every galaxy that we look at seems to be on the red end of things. So it must be moving away. Large scale expansion. Everything's moving away in every direction. Okay, it's amazing. Now, The relative abundances of the elements, that's sort of a abstract kind of a concept here. You know, you would think everything would be iron if that's what everything goes to and then drift away from it. But you got a lot of those heavy elements out there. Well, that's not enough to be supported maybe by all these supernovas. So there had to have been something back there to make these really heavy elements. Okay? And then you have things like diffuse cosmic background radiation that seems to me kind of like this. The Kobe spacecraft or observer that has been measuring this for years, and they've got it out there, and they can't explain it by any other way than there's something happened a long time ago. Now, no one knows where this is going. Here is the most puzzling part of this whole picture to me. And it may be just because we're really limited in our understanding of things, but Newton's second law says the only thing that can create an acceleration is a net force. Okay? The only way you can accelerate something is to add, to give it a force. Something gives it a push to make it accelerate. Okay? And that kind of makes sense. Well, we talked about the large-scale expansion. And if there was a Big Bang at the beginning, I can really understand without friction and other things, things were pushed out and just got going outward. And in space, I can understand the velocity, constant velocity, there's no friction to slow it down. That makes sense. Here's the part that doesn't. Hubble and the others, when they found out this, where was it? I thought it was up here, but the fact that large scale expansion. It's not just moving out at a constant velocity. It's accelerating outward. What is the force that's pushing it outward? Okay? A Big Bang would be, hit the baseball with the bat and the ball takes off. But once it leaves the bat, there's no more acceleration. It just is going. Well, Big Bang, big explosion, but what is making it accelerate now? There must be some enormous force still pushing out. That's part of what they call dark energy. You know there has to be energy being expended, and we have no clue where it's coming from, what it's doing, and we know what it's doing, but we don't have any reason. So, this question, expansion forever? Well, my question, acceleration forever, okay? Answer that one first. As long as it's accelerating, yeah, it's got to be expanding. Or does it go out and finally reach its equilibrium and then start coming back in? Okay? Well, that's sort of like a spring. But as soon as it reaches its maximum here and goes that way, it starts slowing down again until it reaches its maximum here and starts coming back here. We aren't doing that. We're accelerating out, So it's kind of like whatever poet, I don't know. I don't understand it at all, okay? Now, in another chapter, all right, let me sort of catch up where we are. I've not been turning my pages well. Are any of you old enough to remember the movie E.T.?
Never seen it.
Never seen it.
It's
Okay. But a few of them.
memory just in my mind. I don't know, but I have bad memory.
Okay. Has anyone ever seen it?
Yeah.
Did you say you had? Yeah. Okay. Now, what ET stands for is extraterrestrial. In other words, some sort of living form that came from somewhere else.
You mean from outer space?
From outer space, exactly.
Like an alien?
Yeah, exactly. Okay? Read this blurb, you'll see, not likely, folks. Okay? We know no other life form is in our solar system, and it would take us close to a lifetime to get from here to Pluto. Okay? Really. we haven't even left our solar system. To get to the next nearest star, multiple generations of lifetimes. So if someone did come in, they've been in space a long time. You know, I don't know if any life form can live in space that long and reproduce in space. Read this. It's just incredible. Okay? And then the Milky Way galaxy, that's in here. And here she is, Jocelyn Susan Bell Burnell. Okay? And as far as I know, she's still alive. She was born in 43, which would make her, let's see, my brother was 49 and he's 69. So she's in her 70s. Okay? She's the woman who's discovered that first pulsar. Okay? And I don't think it talks about it here, but and she discovered many other things. She was an incredibly brilliant woman, and as far as I know, she's never been recognized as much as she should be. The other picture of the Andromeda Galaxy is in your book, very similar to the one before. Mistakes and misunderstandings. Y'all remember the Star Trek? If anyone ever see a Star Trek show or movie, and Captain Kirk says, call, what is it, command center, whatever that was. I can't remember what they call it. Okay? And she calls, and then maybe a few hours later they get an answer. If it's a few hours later, they were on Uranus. Okay? They weren't a galaxy away. No way. Because remember we said our Milky Way is 100,000 light years across. So what if we could see a star at the other side of the galaxy? That would have meant it took 100,000 years for that light to get to us. So if we were going to communicate with it, it would take 100,000 years for the signal to get there, and then for them to respond is another 100,000 years back. What did you say? I don't remember. Okay, 100,000 years. That was how many generations? And that's across our galaxy. Intergalactic? No. Okay. Remember, that was more like 2 million light years to Andromeda. Okay. Okay. So, to talk to Mars, there would be a 4.3 minute delay. To talk to Jupiter, 35 minutes, more than half an hour. To talk with Saturn, 1.2 hour delay. Uranus, 2.6 hour. Okay, so therefore, think of this. Talk to Uranus, it would be, we send a signal, and we couldn't, at the beginning of class, we wouldn't get an answer back 4.5 hours later. Still no answer, because it couldn't possibly get back to us in time. Okay? Neptune, 4 hours on average. Pluto, 5.3 hours across the Milky Way, 100,000 years, and to Andromeda, 2 million years. Okay. Now, the blurb at the top of 369 is talking about dark energy. Okay? Well, I've mentioned that already. Fascinating read. At the bottom of the page is this concept of the expanding universe. And this is what they see happening. In just a short time that we've been able to measure things and then look at it a few years later, things are going apart rapidly. Large-scale expansion. And they said, picture raisin bread. That you knead the bread, the dough, and it gets in this little thing, and then you put it in the warm oven, and it expands, and the raisins all get further apart. That's what we've sensed happening to the galaxy. And so far, they're accelerating apart. They're not even begun to come back together again. So that's why that picture's there. All right. Now, our book has another illustration. I mean, the old edition had another one. This one does not. Here, when it's talking about the Kobe, I think this is M map, W map. And again, the book tries to do a fairly good illustration of it, but it's just way too deep to do in just a few words. They do have Hubble's law here. I think that's worth writing down, so I think I will. I've got to get my pen reactivated. I thought I had it activated. Okay. Oh, that was on a different thing. V is equal to H sub 0 D. Okay. Now, we're not going to do anything with it, but that is basically Hubble law states the speed is equal to the distance between the galaxies multiplied by this constant. And so when the distance is greater, the speed is greater. That means it's accelerating. The ones further away are accelerating even faster than the ones closer in. That basically is what it's saying. 14.6 and 4.7 use that formula. You don't need to. Now, if you thought the dark energy blurb at the top of 369 was interesting, and it really is, there's a whole page on dark matter, and boy, it just sort of emphasizes how little we know about anything. Okay, we think we're understanding a lot, and the more we find out, the more confusing it sort of gets to be. But the search is fascinating. Okay. Now, there is one more slide in your book that's not on the slide set here. Beautiful slide here. At least 3 possible outcomes for our universe. It looks like 4 to me, but I guess 2 of these are similar to each other. The one is a Big Bang that at some point will then collapse again. The other is a Big Bang that the expansion slows and becomes almost constant. The other, the Big Bang, that it keeps expanding forever. And the final is a Big Bang that the acceleration keeps expanding forever. So it's pretty interesting little graph there. All right. Now, I've already said it today, but I'll say it again because this is where I always say it. Nothing replaces reading the chapters. Nothing at all. I'll make a confession to you. When we used to teach a low-level physics class instead of here, but that wasn't transferable. That's when we were Western State Technical College. We weren't interested in transfer because our people were going to graduate and go to work right away. But when we merged with Lawson, well, actually before that, when we were trying to become a community college and we got approval to do so, we had to come up with a course that would transfer. And I found out about physical science, and that does transfer. So we went from sort of a technical physics to physical science, which has a good amount of physics in it, but then it has these other things, chemistry and astronomy and earth sciences. Well, I was okay with the earth science part because that was part of my background. I loved chemistry, so I had a good background in that. I had never taken an astronomy course in my life. And here I needed to start teaching astronomy. It was a much earlier edition of the book, home with me every night, and every night read as far as I could get, without falling out, ahead of what I needed to do. And I'd read the stuff over and over and over, because some of it I thought they said this back here and here, over and over again. Finally, I sort of felt like I had a decent grasp of it. That's the only way I know of getting a good grasp. Read the chapter. And parts that are confusing to you, read a few times, okay? Maybe look it up and find the other things. Then they have a summary. Now, this summary is a little on the short side compared to some of the others in the book, but it's a pretty good thing. It hits the high points pretty well. Now notice I have a summary of equations, only 3. Most of the time there aren't that many, but in our portion there's not going to be a lot of equations. None of these are very practical, okay, so don't worry about them. I'm not going to test you on those. Key terms, though, those are pretty important. A lot of the key terms you'll find as the italicized word in the summary, okay? The key terms are given in alphabetical order, but in parentheses they give the page numbers where they're found. So if you can't come up with a real good definition for these, go back to that page number, read through that again, and understand. Now, the very best study tool for your test, in my mind, those other things are good. They're important. Applying the concepts. There are 50 questions here, probably a little bit more than normal. 50 multiple choice questions. Now your first test, I think, may have all multiple choice questions, but you're only going to have, I'd say, 15 to 20 questions. Now they're not going to be the same as these 50, okay? None of them are going to be just like this. But the same material is asked about in different ways, and if you know and understand those 50, and by the way, the answers are given at the end. All 50 questions have answers to them. That, to me, is the best way to study for the test. Okay?
Those questions will be on the test?
No, these specific questions will not be. But the material covered by these questions will be. They may be asked slightly different forms, slightly different ways. But if you understand how you get the answers here, you will understand how to get the answers on the test.
Use this as a study guide?
Yeah, use it as a study guide. That's exactly what I'm saying. Other good things to use as a study guide, notice there's questions for thought. There's 21 of those, and that's a few more than normal in most of these chapters. And then there's for further analysis, only 5 of those. Now those, the answers aren't given except in the book. You have to go back and read the book and find out the answers to these. The multiple choice questions are given at the end of those, which you still can look at go back and read the book and understand. All right, Pioneer. Who mentioned the satellite that's out there, kept going and going and going? Yeah, Pioneer was one of those, and I believe the other one was Voyager. I believe so. I don't know. Mariner went to Mars. I know those went to Mars. Okay. Now, there's also some parallel exercises, and these are mostly problems that you calculate using those formulas that I said really weren't all that urgent. If you really want to understand this better, go into those. I'm not going to test you on those. Okay? So, the test will be the last 30 minutes of Tuesday's class, from 3:15 to 5:15 to 5:45. Okay. What time is it now?
It is 3:19.
Okay. So we've got time to start on chapter 15. Would you want to? Okay, we're going to stop and start the lab at 3:45. You want a little break now, or would you rather wait until 3:40 or so? When do you want the break? Now or later? These are both good stopping points. None?
So what you want, class?
Say again? Well, some people have been coming and going. That's fine. You can always do that. But if you want to, everybody get blood flowing or something, we can either do it now or at 3:40. Yeah. Okay. Let's take a break now. I'm going to put this on hold. Please remind me to take it off hold. Okay. I'm going to go and get set up for the next chapter. What's that? Don't forget what? Yeah, I'm going to pause it. And don't forget to tell me to take it off pause. That's the more important one.
Yeah, let's not forget to do the wall call at the 3:45 session.
Yeah.
Like you did the other day.
And that's why I was sort of hoping y'all would say, let's break at 3:40, and then when we came back, I was going to call roll. You'll have to remind me now. But we're going to have the lab, so that'll be a good reminder. Okay. So I'm going to put it on pause.